Good evening, everybody, and welcome to my presentation. My name is Sedighe Khaleghzade, and I'm a PhD student at University of Birmingham. The topic of my presentation is interval multilinear system for tensors in the Max-Planck algebra and their applications. My presentation will take about 14 minutes. If you have any questions during the presentation, you may have until the end of my presentation.
I've divided my presentation into 4 main parts. First of all, give you introduction. Second, we'll look at preliminaries and basic concepts. Third, tell you about weak solvability. And finally, I'll explain using Max-Planck algebra to solve job shop problem. So I want to say about that introduction. My first topic, providing Max-Planck algebra for tensors and interval multilinear system in Max-Planck algebra. My second topic, preparing an algorithm for computing multilinear systems in the Max-Planck algebra. My third topic, elaborating necessary and sufficient conditions for weak solvability of the interval multilinear system. My fourth topic, giving some examples, and finally providing the application of Max-Planck algebra in the synchronized discrete event systems, more precisely in the job shop. Now let's move on to my first topic, which are some facts and figures. The term tensor or hypermatrix in this presentation refer to multi-way array. Notice that the notation of tensors used in this presentation should not be confused with field tensors used in physics and differential geometry. The number of the dimensions of a tensor is called its order, that is an M-order tensor. We denote the elements of an M-order tensor by I1, I2 to Im, where Ij and J between 1 and J between 1 and M. If we have these equalities, then it is set A in Rm comma n is an M-order n-dimensional cubical tensor, or for simplicity just M-order n-dimensional tensor. Look at an example of tensor. Tensors are obviously generalizations of vectors and matrices. A vector is a tensor of order 1 and a matrix is a tensor of order 2. This picture shows you a third order tensor y with elements y, I, j, k. This picture is a third order tensor and effectively regards third order tensors as block matrices. Now we have the definition of the J-row tensor Rj. Let's A in M-order n-dimension tensor. We define its J-row tensor Rj as a tensor in M-1 order n-dimension for j in 1 to n. And this picture is the first row tensor y1 in 2 order n-dimension tensor with element y1, j, k. Let's turn now to moving on to Max-Planck algebra. The Max-Planck algebra is the set of R union epsilon, that epsilon equals minus infinity, equipped with 2 operations, addition and multiplications, where addition is this form and multiplication is this expression. Before we tell you about Max-Planck algebra for tensor, let me expand on this point. Let A be M-order n-dimension tensor for a vector x in complex vector. We use this notation denotes a vector in complex vector whose ith component, that is these equalities, and especially when m equals 2, then this notation denotes a vector in complex vector whose ith component is this equation. Notice that the set of all tensors of order m and dimension n over the max plus algebra is denoted by this notation, and the set of all m-order tensors is denoted by this notation. Afshin and others extended the basic max plus algebraic operation to tensor, that the max plus algebra addition and multiplication are defined as follows. Let's give you the definition of interval tensor. An interval tensor is a tensor with coefficients formed by real closed intervals, or in other words, an interval tensor is a tensor where every element is an interval, and this notation is an interval tensor where A bar is upper bound of interval tensor A. Notice that for m equals to I is an interval matrix. I'd like to elaborate on this point for a few seconds. The notation represents a system of linear max plus equation. And so the principal solution of linear system for max plus algebra is defined by this expression. Now let's move on to interval multilinear system. Let AI be an interval tensor and BI be an interval vector. This notation represents max plus interval multilinear systems, and this notation represents each subsystem of interval multilinear system of 1. If underline A equals overline A and underline B equals overline E, so we say that an interval multilinear system has a constant tensor and has a constant right hand side. Now we have the following definitions. For a multilinear system, if we use inequality instead of equality, so we call x bar star is a solution of this inequality, and if this inequality is holds. And the solution set of the multilinear system is defined as follows. So x bar star be solution of this inequality. X bar star is a solution of 2 if and only if for any k there exists this equality. Let's look at the sum notations. The notations x star to denote a solution of multilinear system, and the notation x bar star to denote a solution of this multilinear system. For A equals these amounts and RK equals this maximum, if in chi of A the maximum in definition of RK of A is attained more than was, then we denote these notations. This algorithm highlights the importance of based on the above discussion. So we give the following algorithm for solving the multilinear system, and the first we need to compute of RKJ of A and beta j and alpha I, that we explain how to compute in line 1 to 18. So we have the inequality system, and after solving the above inequality, we have these inequalities. And if two conditions in line 22 are holes, so xj set gamma j. Else, the multilinear system is not solvable. And we check in line 27 if this condition is holds, so we x star is a solution the multilinear system, else the multilinear system is not solvable. For solving the system of linear inequality 5, as you can see on algorithm 2, the first we need to compute this minimum and set alpha s and check if XRL is not a single variable in some inequality of inequality system 5. So insert XRL in part 1 of inequality system 5 and else break to line 11. If the union not equals these amounts and there exists an index f and we check if xf is a single variable in some inequality of 5 which xf satisfied in this inequality. So if this minimum set xf and else this minimum set alpha s. And at the end of algorithm 2 we return gamma 1 to gamma n minimum. In this example clearly shows the main results of weak solvability. So we have the equation, and this equation is a special case of multilinear system. We interize and we find the maximum interize in step 1 and notice that it is possible the maximum in some row of A is attained more than once. So before we find the maximum in the next row, the condition of line 6 to 10 will be checked for other maximum in the same row, and so we compute beta j, and then we have this maximum is equal to 0. In step 2 we compute alpha I and insert in a linear inequality system, and so we have alpha 1 equals epsilon, that epsilon equals minus infinity. In this step we solve the linear inequality system by algorithm 2. Therefore we have these inequalities. So we have in this example in linear inequality system, and finally we check two conditions, and if two conditions are satisfied, so we have x1 equals gamma 1 and x2 equals minus gamma 1, and x star is a solution of multilinear system. Here are some of the reasons for weak solvability. In the first result, we obtain the necessary and sufficient conditions for the interval multilinear systems with a constant tensor to be weakly solvable. Then by definition of the canonical tensor, we obtain similar results for non-constant tensors. So we call the system is weakly if at least one of subsystem is solvable. What I intend, weak solvability of interval linear system corresponds with the existence A in AI and B in BI. The aim for weak solvability is finding the matrix and vector such that linear system is solvable. And we can be sure that this interval multilinear system is not solvable only if we know that the system of one is not weakly solvable. Keshlarova and others proposed an algorithm for finding a matrix such that for constant vector b, the subsystem of interval linear system is solvable. Similarly, a condition for weak solvability of interval multilinear system with a non-constant tensor can be stated formally and identically for Max Plus using a canonical tensor of an interval multilinear systems. Algorithm is the main issue of weak solvability, that for finding the canonical tensor. The first, we have the lower bound and upper bound of interval tensor and vector B. So we compute as this maximum, and we check this condition in line 9, and so we have these equalities, else we have these equalities. And at the end of this algorithm, we have the canonical tensor that is A of B. Now we give some properties of the canonical tensor according to algorithm 2. In this proposition, let interval multilinear system with a constant right hand side and the solution sets of underline A comma B not equals empty. So we have 4 items, that item 1 is equals this expression, and item 2 equals these equations, and item 3 equals these amounts, and item have this inequality. Look at the condition of weak solvability of interval multilinear system such that is not constant right hand side is determined by the following. Let the solution sets of A of B bar comma B bar not equals empty, then an interval multilinear system is weakly solvable if the inequality of 6 is holds. Now in example 2, we explain how to compute the integers of the canonical tensor. Consider the interval multilinear system, which interval tensor and interval vector is this form, and so the lower bound of interval tensor and upper bound of interval vector as follows. By algorithm 1, we consider this inequality system. We explain how solve this inequality system by algorithm 2. In the step 1, we compute minimum of alpha I, so equals alpha 3, and sets in inequality system. So we have this inequality system of 7. Notice that in this inequality, in inequality 1 and inequality 2, 3, 4, and 5, we have the single variable, and so the union of RL not equals 1, 2, and 3. So we compute this minimum between of inequality that x2 is a single variable, and we insert x2 in inequality system of 7, and we have inequality system of 8, and we compute the inequality system that x1 is a single variable and equals these amounts. Finally, we returns gamma 1, gamma 2, gamma 3, because the set of union is equals to 1, 2, and 3. So coming back to algorithm 1, and we calculate x star by algorithm that gives x star equals these amounts. Now by algorithm 3, we obtained Aj prime of B bar. So for example, for j prime equals 1, we have the following, and this amounts equals this equation. Similarly, we obtained R2 of B bar and R3 of B bar. Finally, we determined of integers of A of B bar, and for A11 of B bar, we have the following. Then by algorithm, this amount equals 6. Therefore, the canonical tensor A of B bar is in the following form. Similarly, we get x star A of B bar and comma B bar equals this amounts, and since this inequality is holds, then the interval multilinear system is weakly solvable. As an application of interval multilinear system, we briefly sketch how our results can be used in the Max-Planck algebraic system theory. Max-Planck algebra is an effective tool for modeling discrete event systems, especially synchronized discrete event systems, or SDES. SDES is a problem in which an event is scheduled to meet a deadline. The events run simultaneously, and the completion of the lengthiest event has to compulsorily happen exactly at the deadline. Job shops are a special category of SDES. In a job shop, the flow of resources through the jobs is not identical. That means that each job might not require the machines in the same order for processing. Also, all the machines may not be required by all jobs. In a job shop problem, the number of schedules generated is equal to the number of machines in the system. Now we consider the Max-Planck algebra to job shop problem in SDES as follows. 6 jobs which are within the same market but are located at some meters from each other were studied. The 6 shops find out that customers start buying at 7 o'clock a.m. The 6 shops A to F sell 6 different beverages. That beverage products. That beverage products is usual milk and so on. That we denote by VP, CD, CB, and TC. Notice that the shops work 6 days within the week, that is from Monday to Saturday. Each product has one representative, and the time available, or TA, to the sale representatives to restock the shops depend on when the shops are open to them before the set time 8 o'clock a.m. The TA for reps and the time each rep spent on each product was taken on each of the 6 days for each of the 6 shops. The latest start time can be obtained via the difference between the finish time and individual event duration times. If we are to take shop A, for example, when the shop is open to the reps for V and so on, the time each rep took was these amounts respectively, where they were to finish within 45 minutes. Obtaining the difference implies that the latest starting time for each event is these amounts respectively. After considering the events of all the 6 shops, we will get a multiple deadline. When we consider the case where we have 6 shops, each shop will have different time available to the reps for their respective products. This will depend on the size of the shop, quantity of products available to the reps to restock, time the reps report at work, and also the time the shops are open to the reps to start restock. Below are the tables for shop A to F, various data taken for the respective shops in the selected week. That this table is shop of A. This table is a shop of F. A tensor A, I, J, K be third order 6 dimension such that the index I shows the reps for V and TC. When the shops is opened and the index J shows the 6 shops A to F, the index K shows the shops for 6 days within the week, that is from Monday to Saturday. That BL is a maximum of each TA corresponding to row L of each of 6 shops. For example, for Monday we have B1 equals maximum these amounts, and so we have a tensor A and time available corresponding to each days as follows. The events completed at 7 o'clock a.m. when the shops are open to customers. We need to find the latest starting time for the various products. The problem is formulated as a multilinear system where the entries of A and B are given as shown in the above, with A1 equals A Monday to A6 equals A Saturday and B equals these amounts. Now we use algorithm 1 for calculating a solution of the multilinear system as follows. Due to line 4 and 6 of algorithm, we have these amounts of entry of A, and we have the maximum is this amount respectively. And by algorithm, alpha 1 to alpha 6 equals this amount, and we have this inequality system. So by solving the above inequality system by algorithm 2, we have these inequalities, and by checking of 2 conditions in line 22 of algorithm 1, we have X star is a solution of multilinear system. Notice that as observed in the above, some entries of the tensor A are marked with a symbol to indicate that these entries are used in solving multilinear system. In other words, these marked entries are satisfied in the multilinear system. For example, consider the following equation. So by substituting X star inequality 9, we see that only entries of A1 were marked with a symbol, satisfying in inequality of 9. These marked entries show that the delay time on Saturday is less than for the other days because A6 has the most marked entries. After Saturday, the delay time on Monday, Wednesday, and Friday are the same because on each of these days there are 2 marked entries. Similarly, shop A has the at least delay time among other shops, and Visual Milk has the least delay time among other products. If we compare job shop between interval system with multilinear system, we have the problem is formulated as a max plus matrix equation, then matrix A and vector B formed from the average to show the preparation before a shop is open to customers and the average of time available to the shop respectively. In multilinear system, all entries of A and B have been used. In the matrix case, we can only consider the time delays for 6 products and 6 shops, while in the tensor case, the time delays for the days of the week were also considered. In this talk, the focus is on third-order tensors. However, our approach naturally generalizes to higher-order tensors in a similar manner. To conclude, I'd like to say the max-plus algebra system of interval matrices has been studied widely in the literature. In this talk, we propose the interval multilinear systems for tensors in the max-plus algebra. We have developed an algorithm for computing the multilinear system and used for the job shop problem in a synchronized discrete event system. And the weak solvability of interval multilinear systems in max-plus algebra have been studied. The results obtained have shown that the method is very efficient for solving multilinear max-plus systems, and it's also applicable to job shop problems. This talk is based on two following papers.
Thank you so much for being such an attentive audience, and I would like to thank Professor Stefan Gabert for his helps. If anyone has any questions, I'll be glad to answer them. If you want more details, you can connect with me by my email that is here.